We're good to go? Okay. Hello, everyone. Thanks for coming today. I'm going to present a joint work with Anne Boyard, who is not here today, and Céline, Comte, and Fabien Mathieu, who are both here with me and are going to talk, hopefully. So we're going to talk about kernels and queues and an approach based on analytic combinatorics. Network calculus aims at computing error bonds on the performance on queuing systems. And usually it's done using probabilities and max plus algebra, and those are the classical tools. But today we are going to use a different one, analytic combinatorics. And the reason for that is that recently there have been many interesting results and tools developed to analyze random walks using analytic combinatorics. I will explain what analytic combinatorics is in a next slide. So for example, the Kernel method is one of those tools. And walks looks a lot like queues, actually. If you have a walk in a quarter plane, for example, you can, and a system with two queues, you can imagine that the abscissa of the walk is the number of people in one of the queues, and the ordinate the number of people in the second queue, and so you have a kind of bijections between them. They are not always perfect bijections that work well in the boundary cases, but still the tools can apply, so developed from one case can apply to the second case. So that's what we are trying to do here. And we are not the first one to believe that's a workable idea. This works, this does not work. Wow, okay. Guillemin and, for example, and also there is a book from Fayol and co-authors, also used a lot of tools with generating functions and analytic combinatorics to study directly queuing systems. So that's the kind of things we are going to do. And first I'm going to talk about analytic combinatorics, what it is, and then we will see applications to queuing systems. So the typical kind of objects we count in analytic combinatorics are, say, trees. For example, here, ordered trees. Ordered means that there is a root, that's the red point, and the children of each node are ordered from left to right, say. And the typical question is, how many trees do I have with n vertices? What is the asymptotics when n goes to infinity? Or things like, what is the limit distribution of the number of leaves, for example, of a random tree? And to answer those kind of questions, the particularity of analytic combinatorics is to associate to the number of, so there is this sequence of numbers. T0 is the number of trees with 0 vertices, so here it's 0. Then there is T1, 1 vertex, T2, 2 vertex, T3 is equal to 2, there are 2 different trees, T4 is equal to 5, and so on. And to study this sequence, we introduce its generating function, T of z. So z is a formal variable, and so the coefficients are just here. And of course, at the beginning, we don't know the sequence, we don't know the generating function. What we know is a combinatorial description of the object. Here, the combinatorial description would be what is an ordered tree? It's a root and a sequence of children, which are themselves trees. And this description is going to be translated into an equation on the generating function that characterizes it. And then once we know the generating function, we can extract information on the coefficients. So that's the idea of analytic combinatorics. And to do this translation, we will simply translate the combinatorial operation that I mentioned one by one into analytic operations. And this is done using what is called the Symbolic Method. And if you want to know more about that, there is an excellent book by Flageolet and Sedgwick available freely online. So you can go learn more there. So here I'm going to explain a bit how the symbolic method works on two operations. So we have those combinatorial operations, and we want to translate them into operation on the generating functions. So say we have two families, S and T, S like cycles, for example, and T are the trees. And we have the corresponding generating functions. Then maybe we want to consider the disjoint union of the two families. So U would be, an object in U is either a tree or a cycle. And this is very simple. How many objects in U do I have with n vertices? Well, it's the sum of the number of objects with n vertices in S and in T. So when I write this down, I obtain simply that I obtain directly that the generating function for U is the sum of the generating functions. Meaning that this proves that the disjoint union, which is a combinatorial operation, is translated into a sum on the generating function. That's not a big surprise, it's really simple. Now with the product, the Cartesian product is a bit more interesting. Say that the objects in U are pairs where the first element is a cycle and the second element is a tree. And I want to know how many objects in U I have with n vertices in total. So the n vertices have to give part of them to the cycle and part of them to the tree. So say I have P vertices in the cycle and Q vertices in the tree, then the sum must be n to have n vertices in total. And when I ask myself how many objects in U do I have with n vertices, then I obtain this simple formula here. And I recognize simply that this is the product of the generating functions. So the Cartesian product is translated into the product of generating functions. And actually it's the other way around. We wanted to have this nice property, so that's why we defined the generating function like that and not in a different way. So yeah, that's the partial conclusions. There exist other combinatorial operations we know how to translate into generating function, but we will here need only those two very simple ones. And what I said about counting things, here Sn and Tn were the number of objects of a given size, it also works with probabilities, of course. So here, let me give you an example, the Galton-Watson trees. So a Galton-Watson tree is a tree we start with a root, the vertex, the root, and then we draw at random its number of children. So there is a probability phi 0 to have 0 children, phi 1 to have 1 child, phi 2 to have 2 children, and so on and so forth. And then again, I do the same process with independently for each child. So that's a Galton-Watson tree. And I can describe it by saying it's either the root alone, R, or a root with one child, or a root with 2 children, and so on and so forth. So that's disjoint unions. I know how to translate them. That's a plus. So I translate that. I say, oh, there is a probability phi 0 to be in that case, and the generating function for just a root, that's just the variable z. Do you see why? Because a root, there is one object, and, well, it contains exactly one vertex, so it's size 1. So it's 1 times z at the power 1, so it's just z alone. Okay. So the generating function for R is just z. Plus, this is a Cartesian product. That's a pair of elements. So I know how to translate that. That's a product for my generating functions. So this case has probability phi 1, z for R, and t of z for t. And that's the product. And I translate that again and again. And if in this line I factor by z, and I introduce the generating function for my numbers phi I, I obtain this very simple equation that characterizes the generating function for Galton-Watson trees. T of t is t times phi of t of t. And from there, we can extract exact expression for the probability that a tree has exactly n vertices. That's the coefficients, nth coefficients in z of t of t, by definition of the generating function. And using Lagrange inversion, a black box theorem, I can tell you that it also has this nice expression that involves not t of z anymore, but only phi that we are supposed to know at the beginning. We can also obtain asymptotics using singularity analysis. So this is the result here. I will not show you those black box theorems. We don't need them. We just need to know that they exist and that we can apply them. So tau is a solution of this equation. And then, well, you obtain this formula for the asymptotic probability to have n vertices. So how singularity analysis works in just very fast. The idea is that the asymptotics of the coefficients, the information about these asymptotics, can be found near the dominant singularity of this function. So you look at this function on the complex plane. You go from 0. You look at the radius of convergence. You look at what it looks like near its radius of convergence on the real axis, and what happens there tells you things about the asymptotics. Here. Okay, that's all I had to say about analytic combinatorics.
Thank you. Okay, thank you. So hello everybody. Right now I will be talking to you about the single server queue and the relations with analytic combinatorics. So first, just a reminder, what is a GID1 queue? In this case, we'll be in discrete time, so we'll have time slots starting at time 0. The queue is initially empty, you don't have any customer in it. And then during each time period, you will have the server that will process one customer on one packet if you have one packet in the queue. And then after that, you will have some random number of packets that will arrive. So we'll just write xt for the queue state. It will be the number of customers or packets in the queue at the end of period t. So first, also we'll define a, that will be the generating function of the number of arrivals at each time slot. So we assume that the number of arrivals at different time slots are independent. They have the same distribution, and this distribution is described by the generating function a, so that so you have a of u, which is the sum of the an u to the n, and an, it's exactly the probability that you have n arrivals at some time slot. So quickly, I said we start with x0 equals 0. Then if we have 2 arrivals, which happens with probability A2, then we have 2 customers in the queue. During this time slot, the server will process 1 customer. Then if you have 3 arrivals, you will have 4 customers in total in the queue, and so on and so on. And so this queue state xt, it is a Markov chain on the set of the integers. Okay, so that was for the definition of the queue. Then the generating function. Here we'll have a generating function that will describe the queue state xt, and this generating function, it will take two formal parameters, u and z. So u, it will be the formal element that will represent the number of packets in the queue, and z, it will represent the time period. So here in my definition, phi of uz, it is the sum over n, which represents the number of customers in the queue, of the sum over t, which represents the time slot, of the probability of having x and n customer at time t, times u to the n, z to zt. So if we just want to understand a bit better this generating series, if we extract the coefficient of z to zt, we'll obtain the sum over n of probability of xt equals n u to the n, which is exactly the generating series of the distribution of the queue state at time t. So you look at one time t specifically, and you take its generating series. Now if you take u equals 0, you will just remove everything that is not at the power n equals 0 in the first generating series, and you will obtain the sum, that probability of xt equals 0 z to zt, which is associated with the probability that the queue is empty at an arbitrary time slot. And finally, we can look at phi of 0, 0. You remove everything but the coefficient of u to the 0, z to the 0, which is the probability that the queue is empty at time 0. and by assumption we have assumed that it was empty, so it's equal to 1. So that was for the generating series. Now, Elie talked about random walks a few minutes ago. We can do a parallel between our queue and a random walk, and it's just an easier way of describing it. So on the abscissa, you have the time t. On the ordinate, you have the number of customers or packets in the queue, and you will just write the number of customers. So initially we have 0 customers, then if we have 2 arrivals, which happens with probability 2, we go to n equals 2. We'll just remember the probabilities by writing them on the edges, and so we can continue like that. Then we have 1 packet processed. If we have 0 arrival, the state decreases by 1, and so on. So we can continue like this. Just so when we are at some point which is not 0, if we don't have any arrival, we will decrease by 1. Then we can stay at the same level or increase. We will always have the same pattern. So here, let's say that we only have 0 arrivals during the next time slots, so that we go back to 0. I just wanted to make you remark that in this case, when you are at 0, since you don't have customer in the queue, the number of customers in the queue can't decrease, so you will have a different type of step. Here, if you have 0 arrivals, you will stay at the same level. Okay, so this was, so you have a parallel between the queue state and the random walks. And what you can see here is that if you look at the probability of having this exact realization, like having 0 customer, then 2, then 1, then 4, then 3, and so on, that's exactly the product of the weights of the edges. So that's exactly A2 times A0 times N3 and so on. So you can say that the probability of having a given sequence of steps up to some time t is equal to the product of the weights of the walk. And more generally, if you want to look at the probability of having a given number of customers at a given time, that's just the sum of the weight of the random walks that end at this point. Okay, so now we can translate our generating series in terms of random walks. In general, that's phi of uz, that will be the generating series of an arbitrary random walk. Then at time t, that they're just the walks of length t that end at an arbitrary ordinate. The MTQ, it corresponds to the walks that end at height n equals 0, and so on. So given this, the next step will be to try to find an expression for phi of uz, and to do that, we'll derive an equation that is satisfied by phi of uz, and then we'll try to solve this equation. So how can we find an equation? We'll use the symbolic method that was introduced by Elie. Phi of uz, that's the generating series of all the random walks. And if we want to look more specifically at the shape of a random walk, what can it be? It can be either an empty walk, just a point at the origin. Then otherwise, it will be a non-empty random walk, and it can have different shapes. First, it can be an arbitrary number of steps that end at a height which is not 0, followed by a step which corresponds to z a of u minus 1, which is a step where you can have one step on the right, you can have some arrivals, and then you also have a departure in the queue. And another possibility is if you have a random walk that ends at height 0, then you will only have another step and some arrivals, so that the z a of u. So this is some equation that is satisfied by our phi of uz. We can rewrite it slightly differently by gathering the phi of uz and the phi of 0z. And that's okay, so that's what we obtain. Now how can we solve it? That's where we'll apply the Kernel method, which Elie talked about. And to do that, we'll first cancel the left-hand side of the equation, and this will allow us to obtain the expression of phi of 0z, and then we'll re-inject this phi of 0z in this equation, and we'll use it to derive phi of uz. And so how will we cancel the left-hand side of the equation? We'll find a way of cancelling this kernel. That's what I have pointed here. So the idea is to choose some u, which will be a function of z, u of z, that will cancel this kernel. Okay, so this is our equation. We take u of z that cancels the kernel. It gives us z a of u minus 1 equals 1. That's exactly the same. So first, we have we can rewrite it as u of z equals z a of u of z. And if you remember what Elie said, that's exactly the equation satisfied by Galton-Watson tree with children distribution given by the generating function a. So we have information on this function u of z. We'll write it ta of z for tree with distribution a. And second point, if we do the replacement in the first equation, we have 0 on the left-hand side, and on the right-hand side, we can make a lot of simplifications using the equation satisfied by u. We know that z a of z, u of z minus 1 equals 1 by definition of u. Okay, so this gives us an expression for phi of 0z, which is just 1 divided by 1 minus u of z. We can write it like that. And so now we can inject this back to the first equation, and we can derive the expression for phi of uz. And so I'm almost done for this part. I would just like to give you some intuition on why we have this shape for phi of 0z. So as I said before, phi of 0z, that's the generating function of the walks that end at height 0 at an arbitrary time step. And so if we look at one particular realization that does that, we can break it up into different parts so that each part starts and ends at 0, but doesn't come back at 0 in the meantime. And that's what we will call an inter-empty period. It makes sense for the queue. And so if we focus on one specific inter-empty period, we can build a tree as follows. The first time slot of the period will be the root. Then the children of this time slot will be the time slots where you process customers arrived during the original time slot. So here, during this time slot, you had 2 arrivals. If we do a FIFO processing, then these 2 customers will be processed during the next 2 time slots, and so on. And therefore, we can build a tree, and we know that the distribution of the number of children in this tree is indeed given by A, the number of the generating series of the number of arrivals during one particular time slot. Okay, and now, Fabien.
Okay, so hello everyone. We'll continue from here. So we saw a lot of things. We will just refocus on the situation of the GG1 queue. So what we saw is that the behavior of the queue, actually, the generating function is quite easy to describe because it's what do you do? How do you understand the generating function? Well, when you start, it's empty. That's V1. Then, if your queue is not empty, that is, if your queue is not in the state 0 for U, then you remove one element, and this in the symbolic system, you just divide by U. Otherwise, you don't do anything, so you keep the empty state as it is. So with this, you removed one element. Then you add another element, and you move one step forward in time. So this is actually what you saw, how you could interpret that. And so if we rewrite that, we have this simple expression for phi. But the question was to compute phi of 0 z. And this is what Céline showed you with the Kernel method. So you could prove that phi in 0 was 1 divided by 1 minus T of z. Okay? So basically, when you've got that, you just have to re-inject the expression of phi 0 z into the equation, and you get this formula. So basically, here you have all what you need. But now I will try to explain you how to use that in practice. Well, first you do a little bit of cleaning. It's easier to solve this expression like this with one simple term mu over mu minus the a of u. And then this will be the tricky term that we will investigate. So this is my understanding of Elie's approach. So it is a Jedi trick, maybe a Elie trick. It's, like I said, when you want to understand what happens asymptotically, you just try to locate the main pole, the smallest pole of your generating function, and you dig into it. So here, believe me, the main pole is 1 for z. So imagine u is fixed, so you just investigate the time aspect of a generating function. And if you want to have that, you've got to look what happens when z goes close to 1. And so I remove z, I remove z, I remove z everywhere, except here, because this is where things become funny. This is where the pole is, here. Because near 1, t of 1 is close to 1, and this is where we have to look. And so I don't remember the name of a trick you said, the black box. Yes, yes. This is where you need to do the singularity analysis. So you can use it as a black box if you want, and just it tells you that to compute this, it is 1 over the derivative of TA in 1. And T of 1, it's T prime A of 1, you can compute it. It's basically, it gives you this expression, 1 over TA of 1 prime is 1 minus lambda. Just trust me on that. Okay, so time is out. We now have this expression, and this is actually the description of the generating function of the stationary distribution. Basically, what we did there was just to try to see what happens when the time goes to infinity. And for other people in other related world, this is what we call the generating function for the stationary distribution. So 1 minus lambda times a of u times u minus 1 over u minus a of u. Okay? And here I will make a brief intermezzo. So this function, it was actually already known. So it's the Polacek-Kitchin formula. Yes. And actually, you didn't need all what was presented before to obtain this. It was very easy to obtain because when you've got a stationary distribution, what happens is that just when you move from t to t plus 1, all things stays alike. And this translates is an equation. So for the stationary distribution, what happens? If the Q is not empty, you remove one element, you divide by mu. Otherwise, you do nothing. And then you apply the multiplication by A. So when you've got this, you just rearrange the term. P of 0, it's actually simply the probability that the Q is empty, and it is straightforward to see that it must be 1 minus lambda. So if you remove P0 by 1 minus lambda, you get exactly the formula from before. Where it was there. Okay. So why, brother? Why? Well, actually, here we made it very simple. I mean, imagine when you want to learn, for instance, about recursive function. What's the first things you do? You write the Fibonacci equation, and you use fib of n is equal to fib of n minus 1 plus fib of n minus 2. And when you know about this stuff, you know that it's stupid. no one wants to compute the Fibonacci function by using fib of n is equal to fib of n minus 1 or plus fib of n minus 2. There are much easier way to do this. But why do you do this? You do this to show the possibilities. And here, there are a lot of stuff that are very promising in terms of possibilities because, okay, at some point we looked at the stationary distribution, but actually we had all the information about what happened before. So in particular, with this approach, we can, from scratch, prove the very existence of a stationary distribution. And if we want to get more information about how fast you converge towards the stationary distribution, you can extract this type of information from this approach. This is something that you can't do if you start by assuming the existence of a stationary distribution. So this is where we can be more than just a simple, more complex version of the Pollack-Keating formula. Okay, so let's go back because we want to have some performance evaluation. So, for instance, we want to compute the probability that the queue has an occupancy greater than some value R. So you just write this. So basically, you want to estimate the probability to be greater than R. So there is a generating function for that. So you see lots of terms with R and N that depends of R. So I won't do the puzzle here, but you can try to rearrange the terms to make appear the expression of pi and reorder the u that are left over. But if you do some rearrangement, basically you get this expression. So the generating function for the error, for the probability to have more than R occupancy, is just a variation of the generating function of your Q. Okay? So now, what do we do? Well, we first did the Elie trick for time. And now we will do the Elie trick for the occupancy. That is, this is the function of mu, and we will try to see the main pole. So you may believe that 1 is the main pole, but actually P of 1 is 1, and so it cancels out quite well. So we have to look at another pole, and the pole is in pi, and it's the second solution of the equation mu equals A of mu. So this is the dominant pole. So we call that beta, the second solution of this equation. And to get the behavior, we have to zoom in to study the behavior on beta. So I won't go into the details of the singularity analysis. Elie promised me that it was a standard approach to do, so I believe him. And it may be a little bit dirty to do that just on the screen. But just applying the same trick than for the time, but here on the occupancy, you get this behavior. The probability of a Q to be greater than R is equivalent, behaves like 1 minus lambda times this. And so that's it, and we will now continue the talk with Céline again.
Okay, so this is what you have just done with Fabien, and now we'll just look at a second example. So we will stop talking about the single server queue, the GID1 queue that we looked initially, and we'll just present you a second example that we considered in the paper, so a more complex case of a queue. So now we still have a single server queue, but now we have two flows of arrivals with priorities. So as I said before, we still have discrete time. The queue is initially empty, but now you have two flows, and during each time period, if so the server will process one packet from flow 1, if there's any. Then if there's no packet from flow 1, the server will process a packet from flow 2. Otherwise, it won't process any packets. So flow 1 has priority over flow 2. And once you have done that, you will have a random number of arrivals for each flow. So again, just a few notations. X will be the number of packets from flow 1, Y the number of packets from flow 2. Then the number of arrivals are still IID, and we'll take A to describe the arrivals of flow 1, B for the arrivals of flow 2, so similarly to before. Just an example to see how it works. Initially, we have X equals Y equals 0. If we have one arrival of flow 1, 2 from flow 2, then we'll put the arrivals of flow 1 at the head of the queue because they have priority. So we process 1 packet from flow 1. Then if we have 1 arrival for each flow, we'll have 1 and 3 customers respectively, and so on. And now if we don't have any packets from flow 1, then we'll process a packet from flow 2. Okay, so that was for the description. Again, this is a Markov process, and so we can study it as before. Now we have a generating series with 3 variables, u, which corresponds to the number of packets from flow 1, v for the number of packets from flow 2, and z for the time period. And so again, we can just look at our generating series to see what it gives. Again, the coefficient z to zt, it gives you the state, the distribution of the state of the queue at time t. The empty queue is phi of 0, 0, z as before. And the empty queue at time 0 is phi of 0, 0, 0. Now, if you want to look at the realizations where you don't have any packets from flow 1, that's simple. You just have to take phi of 0 vz. So you just cancel the variable that corresponds to flow 1. And similarly for flow 2. So doing that, we do the same procedure. We find an equation that is satisfied. Sorry, there's a typo. It's phi of u vz. So we find an equation that is satisfied by phi of u vz. By doing symbolic analysis. So first, if you look at a realization of this process, now either it's empty, you don't have any step, so it's just 1 as before. Otherwise, it can be a realization that ends with some packets in the from flow 1. In this case, you will process a packet from flow 1. That's why you have the u minus 1 at the end. Otherwise, if you don't have any packets from flow 1 that corresponds to the phi of 0 vz, then if you have packets from flow 2, you will process one of these packets. That's why you have the v minus 1. And finally, if you don't have any packets, you will only have arrivals. So that's this last term. And so this gives us the equation that is satisfied by phi. We can rewrite it this way. And so now we'll do the same procedure again. We'll try to cancel the left-hand side member, and we'll see what happens for the right-hand side. So it's the same principle, you just have bigger equations. So this is our equation. We'll take u of vz such that the left-hand side is cancelled. So again, it will be that just a bit more complicated, but it's again a solution of an equation that we can analyze. You can show that u of vz, that just ta, so a tree with offspring distribution given by the generating function a of z times b of v. And if we inject this in the first equation, we obtain this after the simplifications. So here we can rewrite it differently. We just take the phi of 0 vz on the left-hand side. It gives us this. So here we have a problem because we still have phi of 0, 0, z that we don't know. So we have two options. First, we can apply the kernel method a second time to cancel the left-hand side member. Other option, we can use what we know on the queue. If we look at this queue, ignoring the flow types, just by looking at the total number of packets in the queue, then you just have the GID1 queue that we studied earlier. So you can give a phi of 0, just a detail. If you want to compute the total number of arrivals per slot, you have the number of arrivals from flow 1 plus the number of arrivals from flow 2, and the distribution, the generating series of this number is just given by A times B. So you can describe it, and therefore you know that phi of 0, 0, z, that will just be 1 divided by 1 minus TAB of z. So it's a tree, a random tree with offspring distribution A times B. And so again, we can inject it back into the equations to get phi of 0 vz and phi of u vz. And that's the end of my part. Thank you.
So, okay, time to go dirty. You've seen lots of formula, but have a right or have a wrong, so it would be nice to check if no mistake were made. And if you remember the type of formula that you had previously, basically you have something like A of mu, very simple to compute, derivative, not so hard to compute numerically. And at some point, you have to compute things like, for instance, the smallest root of some equation x equal f of x. And in other parts, you have to compute the largest root of something like x equals f of x. So f, here you have series with only positive terms, so there are usually a nice function like this, and so you want to be able to compute where are the roots. So how do you do this? For the smallest root, it's actually no big deal, because it's very easy to see that it behaves like a fixed point. So all you have to do is just start from 0, apply f until you can see the difference, and Bob's your uncle. So that's very easy, very simple. Largest root, when I had to do the computation, it took me a lot of time to get it right, because you've got this thing which is called the convergence radius. That means that f of x may lead to very, very strange result if you go too far. So the first step is to carefully find a value of m that is higher than the second root, but still in the convergence radius, or to change the convergence radius another way, but I won't go into that. Then you've got to find, to be able to be sure to have the right root and not the left root, you've got to find the minimal value of f of x minus x, because then you'll be sure where to look for to find the second value. I see François is very well. So basically you're like this. If you can find the minimum value here, you will know that you have to look there and not here. So you got to do this. And there are many possibilities to do that, but if you have only access to numerical evaluation of your function, and here most of the function you have they are implicitly defined, so you can only access them numerically. Well, there's one possibility that works actually quite well. It's just to use a golden section search. So it's a very nice algorithm. If you don't know it, I'll be glad to explain it to you later, but not here because we don't have time. But basically, it gives you a simple and efficient way to find the minimal value of a function. And when you've got that, you just finish your move by a simple dichotomy. You've got a value where you know that it is below 0, a value where you know that it is greater than 0, and you dichotomize. You know that it is monotonic in between, so you just have to do a dichotomy. And so this is to get the numerical value from the equation, but it's also nice to validate by simulation and not to simulate by validation. Sorry, it was an invention. So how do you do this? Well, like for the formulas, you start from the empty distribution with probability 1, and you just evaluate the evolution of the distribution with time. That is, at each step, what do? You shift your distribution by 1, and you keep what you add in 0, of course. Then you compute the effect of the new arrivals. And here it is very nice because in terms of simulation, it's just a convolution. So one convolution in one dimension if you just have one type of queue. And if you have two queues, you use a two-dimensional convolution. But very easy, very simple. And you continue. So you've got an evolution of a distribution, not a realization, but an evolution of a distribution. And you just wait for the convergence of the distribution up to a given threshold. Very simple. And just because I'm here, so I must show you some curves. We will show you a few curves. So you assume that the first queue, when there is just one, is described by either nothing happens or 6 packets arrive at once with probability 2/30. No, it was just 0 or 6, and we wanted the lambda, the arrival rate, to be 0.4. If you want to know why, where these numbers came from. And B, it's also a queue that arrives with intensity 0.4, but here it's only 1 by 1. So in A, they arrive 6 by 6. In B, they arrive 1 by 1. And in both cases, the intensity is 0.4. So if you just have A, one single queue, this is what you observe. So this is just the slope given by beta, which is very simple to compute. This is what you get from the Kernel formula. And this is the actual distribution. So we're quite happy because, okay, initially we don't have a good estimate because, well, it's an asymptotic behavior, but we fit perfectly for large occupancies. And this is important because we don't have just the slope. We also have the factor to estimate precisely the performance. This is the second example, the one gave by Céline. So now we have two queues. So the first queue, because it is with high priority, we don't have to care about it because it will be exactly the same curve than here. So we just focus on the second queue. And this is the performance of the second queue. And then again, you see that you have a perfect fit between the Kernel formula and the simulation. And I insist in the fact that this is cool, the slope is cool, it's easy to obtain, but it's not enough to have efficient performance validation. Because, okay, it behaves with a geometrical decrease, but you won't be able to tell if the probability to have more than 20 if it's 1% or 1 per 1,000. You can't say. With this approach, we can. We can because we have a factor. We don't have just the slope. And so that's pretty much all I have to say for the numerical evaluation. And now it's time for kitty development with Elie. Merci.
So, yes, just to summarize what happened since the beginning, we saw we had a fast presentation of analytic combinatorics. Then we saw how to use that to analyze a very simple and classical example when there is only one queue and one server, and that we can find again the classical results Polat-Tegichin formula. Then we saw a second example, more complex example with, we saw with Céline how to obtain the generating function, and then with Fabien again we saw how to extract from the generating function information using singularity analysis. And then we saw a second example, a bit more complex example, where we had to use twice the Kernel method. And then we checked with Fabien that numerically, yes, everything looks fine with the simulations and actually the numbers. Now I would like to show briefly a more involved example. It's still a work in progress, but it's interesting because it's not only the Kernel method this time, just to show something different a bit. It's the Keating process. So in this process we have two lines. Let's say those are products, and we want to make kits of products, selling them together. That's what the server is doing. So it's going to serve one client in each queue if both are non-empty, and if one of them is empty, then it can do nothing. It cannot build a kit with only items from one side. It has to take one in each side. And so this translates again into a generating function. U is going to mark the number of items in the first queue, V on the second queue, Z is going to mark the time. And so we have three cases to consider. Either we are at the very start at time 0, so the queue are empty and this is this one, or we can represent what happens in there is a unique way to decompose what happens between we were at some state here and we added and time one time slot. Sorry, I got confused. So the blue thing corresponds to the case where both lines are non-empty. This is, well, a state. Mine is the case where the first line is empty. Mine is the case where the second line is empty. And, well, I just subtracted twice the case where both lines are empty, so I have to add it just to balance things. And in that case, well, I serve one client from the first queue, one client from the second queue. Time goes on with Z, and there are clients or items coming in both queues. In the second case, where either the second line is empty or the first one, but I counted again twice the case where both are empty, then I don't serve anyone. I can really organize this like that. And of course, I want to apply the Kernel method here. Again, I love it. So I'm going to do that. I'm going to find, say, U as a function of V and Z, so that this guy vanishes. So here I'm going to make a simplification. I'm going to assume that there can be at most 2 clients arriving in the first line. So just so that I can actually compute. So this becomes a polynomial of the order 2, and I can actually solve it. And when I solve it, you know, polynomials of degree 2, they tend to have 2 solutions. So one will be denoted U plus and the other one U minus. So for both those solutions, when I inject them into this equation, I obtain an equation that looks like that. Because this guy is 0, this guy is now 1, because it's the same as here, and so I reorganize things, and I obtain this. And what I see here is this guy, I'm not happy with this guy. I cannot apply the Kernel method again to progress in my analysis here. I have to find another trick. Also, I should mention that, yes, if I knew, say, phi of 0v, then by symmetry I would also knew phi of u0, and I would also in particular knew phi of 0, 0. So I could inject them into this equation and find again the generating function for my whole system. So if I break one of those, everything falls down and I solve my problem. Okay? And this is where we apply an idea from Guillemin and Pichon. We are going to play a bit in the complex plane. So I'm not going to give a lot of details here because we don't have a lot of time. So this is the equation we start with. And the idea, that is a very beautiful idea, is to find a parameterization of V and U of Vz such that, so V is going to be on the real axis, and U of Vz, so when V is on the blue, U plus is going to be this half circle here. And another parameterization is when I take V, I parameterize it using a new variable x, and goes like that. Then U minus of V and Z is going to be this guy. So, yes, so when you look at the function U in the eyes, because we actually have it, it's a solution of a polynomial of order 2. So we have the expression, and we can see this behavior. And it's going to be very useful because that means that when in this equation I inject this parameterization and I take the imaginary part, because V is real, those guys are going to be real, and they vanish when I take the imaginary part. And what I'm left with is just the imaginary part of this guy here and the imaginary part of this guy here. And here, everyone is known here. The function V and the function U are both known. So V plus or V minus, U plus or U minus. And so the conclusion of this trick is that basically what I'll just show you is that we know the imaginary part of this function, there is a third argument z that I didn't wrote down because otherwise my equations are a bit ugly. So I know the imaginary part of this function on a circle. And when you know the imaginary part of analytic function on a circle, actually you know the analytic function everywhere. There is a formula called the Schwarz integral formula that gives you back the generating function. So once we have this guy, we find again all the other guys. And the formula is a bit big. There are sum of two integrals, but so I don't show it here. But we have it, and that's what is important. And so what is left to do? Well, first, so we have the generating function for the Keating process, but having the generating function is not the goal. It's just a mean. What we need now is to extract information, extract typically the limit distribution for the number of items on both queues, those kind of things. It should not be a problem. Typically, the black box theorem we have are very powerful and can do that, but we have not done it yet, so I can't promise anything yet. And also, yes, we studied this particular case, the Keating process. So we serve one client in each line, and when they are empty, we do something different. We could try to generalize that to other policies when one of the queues is empty. For example, there is a ski school problem where there are people waiting for to go skiing, and you serve one in each if they are both non-empty. And if one is empty, you serve two from the other lines because you have more capabilities then. So that would be different, but that should lead to the same kind of equations. Actually, we have the equation. And so the same tool should apply. The methods are quite robust. But it's not done yet, so no promises again. It's a work in progress. And so, yeah, what are we doing here? We are actually collecting tools and collecting examples where those tools apply and trying to solve those small with two queues problems. That's very cute, but that's not the end goal. The end goal, of course, is to at some point say, oh, we have enough tools now, we can generalize them and try to deal with big systems with many queues. But to get there someday, we first need to look at all those cases when there are priorities, when there are those different behaviors that can happen with queuing systems. So we are still at a young stage of research, and hopefully we'll get there. That's all. Thank you. Is there some questions, the audience? Jim.
As you said, this is being done. I mean, this studying generating functions for queuing systems. This was a classical way of looking at queuing systems a long time ago. So, I mean, are you sure what you're doing is really new?
Yes. Well, the results on works on the quarter plane, for example, there are some new techniques that are quite recent. So yes, I have not. The Kernel method is well.
In my memory, I'm old enough to have a memory of the time when people used to do this. People didn't react file, and they still do, I guess. But people came to the conclusion that this was a bit too complicated. That in the end, you're going to use some numerical methods to get the solution. Why not just solve the Markovian equations numerically in the first place? That's one possibility. Another possibility was that in order to study more complicated systems, which you just hinting at here with its kitting, it gets very messy. From my opinion, it gets messy. People invented different ways, and I was thinking of someone called Mathieu. I don't know if you've heard of him. He was quite expert in this area, but eventually came to the conclusion that he wasn't getting anywhere. I was kind of looking for these roots of the kernel and whatever. He invented something called matrix geometric methods, which were much more efficient numerically and more general. So I don't know if you think of that. But in general, as an engineer, I mean, are you trying to convince me that I should think of queuing problems or the like in these terms? Is this going to be a practical method? I'm skeptical about that. I still think, especially now as we've got powerful computers which solve numerical equations very rapidly, that why should I bother?
Yes, you're right. You should not compute anything mathematically anymore. You should only do simulations now. Math is completely useless. And when you have a system that is too fast, for example, things are happening too fast. You know, you have to decide the size of your servers at the time things are happening, and you cannot do the simulation because it's too long. Solving a mathematical problem could do the trick. So, you know, solving math is always faster than doing a simulation. If you
set of linear equations, that's it.
Yes.
Equations is also fast.
Mm-hmm.
Yeah.
So yeah, that's supposed to be what math is for. It's supposed to be.
I mean, give you insights. It's supposed to give you closed formulas. I mean, if you get closed formulas, you get insights. Here you've got formulas which are not closed. Really.
Actually, why do even a simulation? We can directly just measure the system.
No, we don't have the system to.
Build a second one. Build a second one.
Yeah, I don't want to. It just surprises me that you reinvent this to some extent. I mean, I was never an expert, so maybe there are new things. Certainly, there are new things you're doing. But
there are many.
This was a very classical way of doing queuing theory when I started to learn something about queuing theory.
Yeah.
In 1970.
Okay. So probably I should give an example on a different field where this already happened before. Enumeration of graphs, random graphs, for example. The old way to count graphs, say count the number of connected graphs with n vertices and m edges, it was done using generating functions. That was, or even before using recurrences on the sequences. But generating functions are nothing more than a nice way to present recurrences, really. And then, so the equations got bigger and bigger, and the paper longer and longer. And then Erdős happened, Erdős and Rényi, and they introduced first and second moment method, and everything was simple again, very short. And so
okay, that's an area where it worked. I'm just skeptical that it will work in the future.
Oh no! I'm not completely finished with the story. So, and indeed, we can derive easily a lot of interesting results on random graphs using first and second moment methods, and yeah, then if you want to be more precise, if you want to obtain, well, different tools have different qualities. Probabilities are great because at the beginning of the problem, you say, oh, this part is not going to be significant for my problem, so I can, you know, forget about it, go at the limit, or things like that. And with the generating function approach, you don't do that. You have an exact expression into the generating function, so it's more heavy, definitely. But you can be more precise. That's the balance between both things. And also, you can build, when you have one generating function representing one object, you can combine it with another generating function because you lost nothing in the process of getting this generating function. With probabilities, it can be more tricky. So, yeah, and that's really my hope with the system of queuing systems, is that we can automatically, at some point, using a description of the system, to obtain system of equations on the generating functions, solve that, decide which kind they are, apply black box theorems there, and get the solution in a more automatic way. But yeah, of course, if we are going to build this big machinery to do that, and we solve small example at the beginning with this big machinery, it looks inefficient. Hopefully we'll get to a point where it will be efficient again.
Just maybe I can add something on this, because yes, here the simulation, okay, they win, but they win because there are one or two queues. In terms, for instance, of space complexity, if you have k queues, and if they're correlated, if they're not independent, you've got, if you want to compute probability to go greater than R, have a space.
It's impressive if you can do R greater than 2, and I'd be impressed.
Yes, yes. So currently, no.
Like Fayol and
Yeah.
Cohen, who studied this, were kind of limited to 2 dimensions because they're in a complex plane.
Yes. And that's one of, so we're not here there, but we want to give it a try.
Okay.
Yes, because 2D convolution, okay, that works. 3D, yes, we can go. 4D, it's already a bother. So yes, this is the goal. Yeah.
So I have another question about the treatment of the single queue that you were asking. So you were claiming to have a general arrival rate, right? But on the same time, is this really a general? How general is the arrival rate? Because as I understand, you treat basically arrivals that have to do with a specific distribution of a number of users arriving. So you say, for example, the probability of 1 user arriving, 2 users arrive, 3 users arrive, etc. Right? So this is like how you treat. So, however, this will not be the case if there is, like, for example, it doesn't capture, for example, a continuous arrival that. You see what I mean? That has
absolutely. Okay.
So how would you adapt this?
So yes, we can absolutely treat the process, the Poisson arrival. We did not present it here, but yes, that's a variant of the generating function. You look at the Laplace transforms.
Case, because this you treat cases where you have memoryless properties. But at the same time, if you start having interdependencies between the interarrival times, then this will not be just a probability on the number of arrivals happening in the interval, but they will have also to do with the distances. You see what I mean? It's only the Poisson that basically you can reduce the statistics to the number of occurrences because the counting process. If you don't have a counting process, then this approach doesn't work. This is what I want to say.
Then it would be more complicated. In the discrete case, you can already consider the case where you have correlated arrivals between 2 time slots. That would be more or less the same ID. And in this case, we haven't treated it. I think you could write the equation, then it would be more complicated to solve it. Of course, maybe we can say something if we have some information on this process. If we know something like when this process goes to infinity, if we have information, maybe we could extract something from the generating function.
Yes, I just wanted to mention that basically I think that it's just for counting process and not for any general arrival process. But of course, if you can generalize it, it's even better.
Yes, I think it was one of the goals for one of the many goals for the generalization.
Calling GI-D1 is in fact MG1, isn't it? Because that's how you find Polychik-Kinchin. The GI generally is general independent interrivals. It's not general independent batches. That's a different kind of queue. And it's a batch Bernoulli process, which turns out to be like an MG1. And that's why you found Polychik-Kinchin. But if you look at GI-D1 with a real renewal process, it's a bit more complicated.
Yes, but just on the silver lining side, we managed to handle the case where you have 2 queues that have correlation between them. For instance, if you have 1 item from A, you increase the probability to have items from B, or inverse correlation. So yes, it's not the full package yet, but at least if for a given time we have correlation between the arrivals of 2 queues, we can manage this. It's straightforward. So yeah, it's not perfect, but that's a start.
And just a suggestion is that maybe if this works very well for the queues, I mean also like an analysis on the caches would also be very interesting. That means a different structure, completely different structure on the way, maybe when you have inventories maybe, for example. this could also be very interesting to see a different, let's say,
Okay, we should discuss that.
Yeah, of course.
Why I'm asking nasty questions. Where did you meet network calculus? I didn't see it on the way here.
Because Anne is not here.
Yeah, okay.
Yeah, she's the one who can explain and justify that.
Yeah. I'd like to see a use for network calculus.
You know that this will be on record. Okay. Do we have any additional question? Okay. So, thank you.